Good morning. Here we are once again in the physics video lecture. Physics 2A video lecture 16. So I had some inquiries about certain homework problems that I'm going to do at the board. If you ever want to see a homework problem worked at the board, go ahead and tell me in your email. Generally, if you want to see it, there's a whole number of people in the class who also want to see it, and they'll be grateful. So let's go ahead and look at a couple problems here. And what did I write? So it was going to be chapter 4, problem 77, chapter 4, problem 79, and chapter 5, problem 7b. So these are all worthy. So for problem 77, we have a sled comes down the hill and then it glides out on the level. Okay. And so really what's happening is it's achieving a certain speed, and they gave us the speed. Okay, so I'm not going to plug any numbers in, but we have V naught here as you know, as we're zipping along. Just draw this. Okay, anyway. We have V sub 0, and then when we come to a stop, we have V equals 0, and we've traversed a distance d. So we're assuming constant acceleration as we slow down. So the formula we use will be V squared equals V0 squared plus 2 acceleration x minus x0. And in fact, with our symbols here, we will have 0 equals V0 squared plus 2 times A times D. So we're just going to hold on to this. That's what happens when something accelerates or decelerates and comes to a stop. But we have to find out, what is the acceleration? A equals question mark. What is the acceleration? And for that we have a free body diagram. I'll use a different color here. So here's our mass, M. It has on it the force of its weight, the normal force, and the friction force, which is opposing the direction of motion. And of course we know that friction force is mu times N. So if we write down Newton's law, F net equals M times A, which is always a good idea to do, and we see the net force here, right? These two are going to cancel, so the net force is pointing to the left. It's minus mu times N, but we know from this set of vectors that N is just equal to mg, right? Equal and opposite, so minus mu mg equals M times A. So now we know that acceleration is going to be minus mu times g. And that's what we're going to plug in the following way. I have some room here. Well, actually, I'll send this up so as not to crowd it. So what we're going to do is solve for the distance in that upper equation. The distance traveled is equal to minus V0 squared divided by 2 times A. But we have an expression for A, so we have minus V0 squared divided by 2 times negative mu g. Minus signs cancel, that's nice because it's a positive distance. And only when you've gotten this far should you even think of plugging any numbers in. So minus sign there, so it's just V0 squared 2 times mu times g. And in this result, we see that if there were no friction, our sled would go on forever. Okay, because put a 0 in the denominator, you get infinite distance. Okay. Good, so that's that problem. Now the second problem that was asked for is very similar to this one, once you set it up. So here we have an idea. There's a crate or a box here, but it's on the back of a flatbed truck. So here's a truck. I'm supposed to draw a truck here. All right. Okay, there's a truck. It's going to accelerate in the positive direction. We'll call that X. Okay. There's someone sitting in there driving the truck. Okay. That's all I'm doing. Here's the thing. We're only interested in the forces on this crate. And as a flat bed, what's actually making the crate move forwards is friction. So the free body diagram for this mass on the truck, you can actually ignore the truck. That's what we're doing. So we have mg normal force. Of course, we're accelerating forward, so the frictional force is towards the front. It's moving forwards. And as always, I'm going to erase this. I'm going to write down Newton's law first. Net force is equal to mass times acceleration. And in this case, the net force is just the friction. That's it. But the friction is equal to mg of mu times n, so mu times m times g, m times a. You see, we're back to what we just had for the other problem. What did they actually want us to solve for in this problem? 79. I think they just wanted, yeah, the acceleration. So this is, oh, by the way, this is the acceleration forward here. It only works so long as there is friction. If there were no friction at all, the truck would move forward and the block would stay in place and therefore slide off the back of the truck as it moves forward. Okay. So since it's the friction moving it forward, there's a maximum acceleration for which that can occur. And this is really what we're getting here. Maximum, so we have, right, it's there, I just canceled out. It's mu times g. Yeah. So there you go. Very similar problem. And finally, problem 7b, this takes us into chapter 5. So let's look this up. Chapter 5, problem 7. Constant speed. Yeah, okay, here we go. So we've done these two. Problem 7, we have a crate that is moving at a constant speed, and there's friction here. And we have a tension force, angle theta. This one we have to be a little more careful. The tension force is up at an angle, and the other force, we have mg, we have n, and we have friction. I don't think I'm going to use any numbers on this one. They gave numbers, and the crate is moving at constant speed. So let's go ahead and write that down. Moving at constant speed. Okay. Now this is important because if we write down our Newton's law, I'll put it in vector form. Constant speed means that the acceleration is 0. Okay. So because of the constant speed here, acceleration is 0, and we have sum of forces in x direction are equal to 0, and the sum of the forces in y direction are equal to 0. Yeah. And we're trying to find the coefficient of kinetic friction in 7b, coefficient of kinetic friction. So find mu sub k. Kinetic friction is when things are sliding. Static friction is when they're not sliding. And we have a mass here. Good. Let's go ahead and write this down now. So we have to do the forces in x and the forces in y. Okay, and that's adequately labeled. X is, of course, the horizontal direction. So in x, we have minus f plus t cos theta equals 0. Okay. And I'm going to immediately write minus mu times n plus t cos theta equals 0. So that's our first equation. Now the y equation is a little trickier, okay? Because in the y direction we have n pointing up, plus we have t sine theta. Okay? There's a y component to this tension. Okay? At this point you should be good at teasing out or figuring out what the x and y components are, but I'm going to get to that. So t plus sine theta are pulling up, minus mg pulling down, there we go, equals 0. So that's our second equation. I'm going to go ahead and relabel this for you guys. And so we've got the, I'll do it dotted, we've got the t cos and the t sine, right? T sine theta, t cos theta. There's our x direction. There's our y direction. So with these two equations, we're ready to solve. And in fact, we have two equations we could solve for two unknowns. We have to get rid of n here, okay? So to find mu, we have to solve for n and plug it in up here. And I have n is equal to mg minus t sine theta. And that's what I'm going to plug in up here. So now I have minus mu times mg minus t sine theta plus t cosine of theta is equal to 0. And now you'll see the only unknown is mu. If I bring this to the other side, I get two minus signs canceled to minus signs, and I can just write down our answer. We have t cosine of theta divided by mg minus t times the sine theta. There we go. So yeah, you want to make sure you can do this. So if you need another line, another step of algebra, by all means just do it so that you can get these answers. So theta was given, t was given, m was given. Right, 175 newtons, 20 degrees, 40 kilograms. And part A was about the work, but work done by the tension force. You know, for part A, this is part B. Okay. Part A, we can just get really quickly. Work is equal to force times displacement but the force and displacement have to be parallel. So in this case, we have T cosine of theta times displacement. Okay. I'll just write here parallel. And then you can plug those in as well if you're interested. Yeah, good. Okay, let's see how we're doing time-wise. Perfect. So yeah, we can always do a problem or two if you guys tell me what you want to have done. We can do them at the board at the beginning of class, and then you can practice these. These were good problems. They were all actually chapter 4 problems. Okay, this was just a little bit of chapter 5. Okie doke. Now we have to get back to where we were in chapter 5. Actually a good way to segue because work and energy is what we've been talking about. But what we ended with was power. We ended with power and the stair climb. And I want to show a couple of important applications of that that'll really help you understand it. So yeah, the good thing about the stair climb example is that you can never forget it. It's so simple. Okay. So we have power is work per time. There are more fine points in the chapter, but I'm really just stressing the basics here. Running up the stairs. And so I'll repeat my stair climb example. Okay, so because work is force times displacement, so since gravity's up and down, the work that counts is really the vertical distance. Now, the work could also be the change of kinetic energy, which we're not dealing with in this example. So note, work could just be mgh. That's really for a constant speed example. Work is also equal to the change of the kinetic energy. Okay. That's definitely also a crucial example of work. And so if you're accelerating and decelerating, there's work involved as well. Change in kinetic energy. So this example is for constant speed, the stair climb example. And when you do that lab, which we used to do, we'll do it again someday, we would actually get a little running start and try to zoom up the stairs at the constant speed and then top out. Okay. And then the work is simply here mgh, so the power is mgh over t. If you do this second form here, I'm going to call this 1, then you would say 1/2 mv final squared minus 1/2 mv initial squared. So if you have to accelerate to get up to a certain speed, you say you may start it from rest, you can call that 0 here. Then the work it took to achieve a certain speed would be in this second form here. Okay, so that's why if you look at some of these problems in the book relating to work, they'll be careful to tell you about constant speed or change of speed. Yeah, in the example we finished this example with some numbers, and we found that a strong person can produce about 1,000 watts power. So this is the example I want to keep going with, though, because it's not just the stair climb. It has some really great applications, generalizations. So my first example is the grandfather clock. Some people know what that is. If you don't, look it up. I'm going to describe it briefly. So the grandfather clock is usually a clock in a tall wooden box, okay? And what causes the hands of the clock to turn, right? It keeps time. Why is it so tall? The reason it's so tall is that there is a weight in here that gets cranked up a certain amount, right? And there's a spool of some kind of string here, and as this thing, and let's just say, since this is hard to draw, there are just some gears that connect all the way to the hands of the clock. Okay. So this weight has been raised, you guessed it, a height h above its lowest position. That's how much string can unwind, or chain, or whatever it is, some length h. And as this thing unwinds, all these gears interact with each other and turn the hands of the clock. And it'll actually run for a week, or even 8 days, so you have to wind it up once a week. Okay. So what keeps the time? Here, let's label this thing. This would be a good one for you guys to look up, print out the good pictures. I've seen resources online where they give a nice description of these gears and so forth. So the grandfather clock, so first point about it is the weight, which is a force, right? There's a weight, there's a tension in the string, that's a force, drives the clock. And the energy stored, did I call this thing M? That's M. The energy stored is just mgh, right? Where have we seen that before? Okay. What keeps time? Interestingly, what keeps time is a pendulum. So there's a pendulum inside the grandfather clock. It swings back and forth. You hear it go tick-tock. And this is also something you have to look up. The pendulum has a thing called an escapement attached to it. So as the pendulum swings back and forth, 1 second over to one side, 1 second back again, then the gears are engaged and disengaged. So instead of the clock, instead of this weight just going down and the thing spinning out in 5 minutes, it takes a whole week. Okay? So I'll just write here, the pendulum is what keeps the time. Pendulum keeps the time. I could bring a pendulum in and demonstrate to you. We have that actually later in the semester. Pendulum keeps the time. In fact, for a simple pendulum, period, I'll just put this here so we have it. Period t is equal to 2 pi square root of the length of the pendulum divided by g. We're going to do this more formally later on. So there you have it. That's a grandfather clock. And the question is, how much power does the grandfather clock use? How much power? So what is the power of this thing, right? The work is mgh, okay? What's the power? Okay, the power, same formula, mgh over t. Now for homework, I want you guys to plug some numbers in. We could plug them in right now, but I don't have a calculator. I will plug them in. I'm going to give an example, a realistic example of a grandfather clock. The mass could be 3 kilograms. Okay. We'll round up and say we have a massive grandfather clock. Let's even say it's 4 kilograms. G, we're just going to use 9.8. We could use 10 as well, meters per second squared. And if that thing is lifted 1.5 meters, that's a pretty big grandfather clock, okay? So we'll use 1.5 meters. And remember, the thing will run for 8 days. That way, you miss a day, you're fine, but you wind it up once a week. So what is the time in seconds for 8 days? You have 8 days, 24 hours per day, and 3,600 seconds per hour. So you could just estimate this right on the spot. This is a very, very small number for power. So I'll just put here equals question mark. There's no reason you guys can't plug it into a calculator and figure it out. You can also just estimate with scientific notation if you want. Okay. But yeah, I want to leave a little suspense here. Go ahead and do this because you're going to be surprised at how little power that grandfather clock uses, even though it's this big. Okay, so that was my first example. Very important one. There was a time when these types of clocks, pendulum clocks, were the most accurate in the world. And so there's actually a whole science behind making these well. Interesting thing. Here's my next example. Check the time again. I think we have plenty of time. Yes. My next example is the hydropower example. This is one a lot of people have been up to some lake. We have many hydropower plants up and down the Central Valley and in our Sierra Nevada mountains. So I'll just list a few in case you've ever been at some of these places. And then I'll explain what's going on there. We have on the Kings River, we have Pine Flat Reservoir. There's hydropower being produced there. Upstream from that, there are a couple. I'm just going to write Balch. And then upstream, there's Black Rock. Some people may have visited these things. Up near the top of the system, there is Wishon and Courtright. These are the big ones. So Pine Flat, it's like between 500 and 900 feet above sea level. And Courtright, the lake is up at, so the lake I think is 900. Courtright, 8,200 feet. Okay, I don't know these in meters. Wishon, 7,500. So these are the water levels. The water levels of these things. Okay. So there's a lot of recreation going on around here. Okay, so fine. Now, what we want to have for our hydropower discussion is just a schematic of what's going on there. So you have a lake behind a dam. You have water here in a lake. You have a dam. And then either at the base of the dam, there's a powerhouse, or thousands of feet down the side of the mountain. In the second case, they run what's called a penstock, and I'll just draw the powerhouse down here. This is where the generators are that generate electrical power, which you'll study in Physics 2B, right? Electrical power. So let's get some color into the mix here. So we've got layers of water. So there's our lake. And down here below the powerhouse, there's always some outlet water as well. Could be a lower lake. For example, this could be Courtright Reservoir. The top one and the bottom one could be Wishon. Okay. So there is a height difference, H, between these two levels of water. and you may see where we're headed with this. This water is potential energy because it's elevated above the lower level, above the powerhouse. So the water has potential energy, and potential energy, which is also work, is just the mass times G times H of the water. You could right then and there calculate, if you knew how much water there is there, you could calculate how many joules of water are up there. I'm going to do a conversion before we're done, but right now, so that's the potential energy of the water. I'll put it here. Potential energy of the water. And how does the power formula work? Same as the grandfather clock, mgh over t. But there's an interesting twist here. Now you could just say the power would be total mass gh divided by time to drain the whole lake, but practically you don't always want to drain the whole lake. You could express this same formula or as m divided by t times g times h. Now this is the flow rate. If you were to read out the units, you would say mass is in kilograms, times in seconds. So it's the flow rate in kilograms per second. Flow rate. But it's the same as our stair climb, the same as our grandfather clock, except that the numbers that come out of this are enormous because we have to power an entire civilization with one of these and not just a single clock. So we'll do a little numerical example on this one as well, just to give you a feel for it. Yeah, you know what, before I do that, let's make sure our cartoon is sufficiently clear. Okay. So this is the elevated water. We could put some mountains in the background and remind ourselves that the way the water got up here was actually the water cycle, right? It came down as precipitation, and so the sun evaporates water, lifts it up there. So it's actually a form of solar energy. So I'm just going to put here, note the water cycle, which is how the water got up in the lake in the first place. Except there's a second way for the water to get up there, and that is called pumped storage. So the lower powerhouse may actually buy energy from somewhere else where it's not being used, at night for example, and they will actually pump water up the hill into the higher lake as a form of energy storage. And we talked about energy storage in the past, where we said if we could just store that work, it would be potential energy, it would be stored work. So that's actually a practical matter in the hydropower world. They buy energy, they run their generators in reverse, okay, as motors, and they pump water up the hill. Okay, so back to a numerical example for this. And I'm going to use some easy numbers. They're realistic. So our example for the hydropower formula is we're going to let H be 100 meters. That's a medium-sized dam. But H can be 500 or 600 meters up in our mountains because they run these pipes way down the hill. Oh, that's something I forgot to mention. It's called a penstock. You can look that up as well. A penstock is what that pipe or tunnel is called that takes the water down the powerhouse. So we're going to let H be 100 meters. We're going to use G equals 10 meters per second squared. That's always good for estimates. And we're going to use M over T equals 1,000 kilograms per second. That's a useful number because that is actually equal to 1 cubic meter of water per second. I'll put this just parenthetically, 1 cubic meter of water per second. Water has a density of 1,000 kilograms. So density, we're getting to that later in the semester as well. It's one of our Greek letters, gross of water, 1,000 kilograms per meter cubed. Okay, but we can take these numbers, 110 and 1,000, and in our power formula, which I'll do right here, working to the left, P is equal to 10 to the third kilograms per second. That's the flow rate. 10 meters per second squared. That's G, 100 meters. And what do we get? 10 to the 3, 4, 5, 6. So 10 to the 6 watts. Okay, 1,000,000 watts. That's a megawatt. Equals 1 megawatt. That's some terminology you should have heard, right? 1 megawatt. Now you've heard it. And I'll just point out that for a large power plant, the output will be on the order of 1,000 megawatts or more. These penstocks are easily and even greater than the diameter of these two boards here. In fact, they could be twice the diameter of these boards. They're enormous. Because, like I said, we're running an entire civilization on this type of power production. So a megawatt, 1,000,000 watts, is something, but 1,000 megawatts, now you're really talking. Okay, but for us, it's easy because it's just another different power of 10. So things scale up and down nicely. You're going to find the grandfather clock was like 10 to the minus 4 or less. Same formula, different regimes altogether. Now, one final thing about energy. What is a kilowatt hour? When you pay your bill, kilowatt hour, question mark. When you pay your energy bill, you pay 25 cents or some amount per kilowatt hour. Okay, and since we're talking about hydropower and hydroelectricity, that is germane. So, what is a kilowatt hour? Well, remember, power is energy divided by time, and that means that energy, I'm going to write it out in words, I could have also said work, is equal to power times time. Okay. So you run power for a certain amount of time, and you have a certain amount of energy, and of course we know that's joules. So in this case here, we have energy, or you could just as soon write W for work, same thing, is equal to 1,000 watts, because that's a kilowatt. I'll write it out, 1,000 watts, that's kilowatt, and the hour is 3,600 seconds. Okay. So what that turns into, 1 kilowatt hour is equal to 3.6 times 10 to the third, 4th, 5th, 6th. So 3.6 times 10 to the 6th joules. This is something we absolutely have to know. And it all comes together this way. I used our definitions and just solved for energy power times time, kilowatts times hours, right? Kilowatt hour. And that seems like a lot for 25 cents, but we use a lot of them, okay? So the reason we use so much energy will become more apparent when we start talking about thermal physics. Right now in the mechanical world, which we're doing this mechanical energy, it seems like an enormous amount. Even a single kilowatt hour. Okay. Good, let's see how we're doing time-wise. I think I'm gonna call it good right here. Indeed. So I'll put a homework assignment up this corner of the board. This is homework for, and this was right, 16th lecture, and we have chapter 5. Chapter 5 problems 50, 56, and 69. 50, 56, 69. This one here, I'll put a little star by it. It's an interesting application of energy conservation. So make sure you use energy on the steps for this problem here. Very interesting. Okay, good. That's it for today. See you guys next time.